Okay, wonderful. So now we're going to use the linear density and the planar density, right? Because we say when we say linear density, when we say two crystallographic directions, they have the same linear density. That means they have the same atomic packing, right? That means they are crystallographically equivalent, right? Even if they are not parallel to each other, okay? That means we have some directions within the unit cell, they are not parallel to each other, but still they are crystallographically equivalent because they have the same atomic packing, the same atomic spacing, okay? And we quantify that by using the linear density equation. We also use the planar density equation, okay? So we can group directions together where the atomic spacing are the same, right? For example, if we are dealing with cubic structure, okay, all the directions that they have the same indices, okay, even if they have different ordering or different sign, they are crystallographically equivalent. What does that mean? If you have a direction that has 1, 2, 3 indices, okay, that 1, 2, 3 direction, okay, is equivalent to 2, 3, 1, okay, even if they have different ordering. What does equivalent mean? That means they have the same atomic spacing. If you look for this direction inside the unit cell, you're going to find the atomic spacing or the atomic packing what here is exactly similar to 1, 2, 3, okay? And even regardless of the sign, for example, 1, 2, 3 is equivalent to 1, minus 2, and 3, okay? Again, what does equivalent mean? That means they have the same atomic spacing or same density, linear density, okay? Okay, now for the cubic system, only for cubic system, regardless of the order, regardless of the sign, okay, if you have vectors with the same indices, okay, they will be crystallographically equivalent, okay? For example, 1, 0, 0 family, we call it family directions, okay, will have, they will have the same linear density, right? If you look, so what will be under this family or belong to this family? For example, we're going to have 1, 0, 0, 0, 1, 0, 0, 0, 1. If you try to plot those vectors inside, plot those vectors, you'll find that all of them, they have the same linear density. Okay, and 1, 0, 0 family direction, they are representing the cubic edges. So if you consider the cubic edges, let's say for FCC, you know that all the edges will have the same atomic spacing. For BCC, all the edges will have the same atomic spacing, okay? Again, we have another family, okay? It was called 111 family, okay? This is a cubic body diagonal. And also we have the 110 direction, family direction. Okay. You can see under each family, we can have many possible or different possible directions. And what brings them together is the atomic spacing or the density, the linear density. I'm repeating myself many times just to emphasize on the point that what is we are classifying the family of directions because they have the atomic spacing, and the way to quantify the atomic spacing is by doing or calculating the linear density, okay? Similarly, we can apply the same concept when you go to the planes, okay? Now we're gonna consider a family of plane if they have the same atomic packing density, okay? Now if they have the same atomic arrangement or the same atomic packing, we call them, they are crystallographically equivalent, okay? For example, and we're gonna have this kind of brackets, which is different than the direction. So we're gonna use a curly brackets compared with the direction. We're going to use an angle bracket, okay? So for the family, we're going to use this kind of bracket, And for the family of plane, you're going to use this kind of bracket. Now, when you say 100 plane, if you look here, the family of 100 plane, you're going to find that the family of 100, they have the same planar density. Because if you consider the green plane over here, okay, let's take the BCC. So for BCC, you're expecting only atoms at the corner. That's it, right? And the area of that plane is similar to the area of the origin of the orange color plane, and the orange color plane still have the same number of atoms, right? Atoms at the core. So then, if you calculate the planar density, you're going to find the planar density of this plane is similar to this, is similar to the red one. So they equal each other. Okay, this is why they are crystallographically equivalent. Now, when we deal with cubic, again, we deal with cubic system, regardless if they have the same indices, regardless of the order or the sign, they are crystallographically equivalent. And this is only for the cubic system. Okay, for other systems, there will be some exception. For example, here 1, 2 minus 3 is equivalent to 3 minus 2 minus 1, 2. Okay. They have the same indices but different order or different sign. Okay, at the end they will belong to the same family. Similar here to when you say 1, 1, 1 planes. Okay, this is very important plane. Why? Because for FCC structure, this is the closed packed structure. This is the plane with the closed packed plane. This is the plane that the most efficient plane where you can bring more atoms closer to each other. Okay, we're going to talk about this plane later. So the family of 1, 1, 1 plane, okay, includes all these different possible planes. Okay, and the common factor between them, they have the same atomic spacing. That means 1, 1, 1, 1 minus 1, 1, 1 minus 1 minus 1. Okay, minus 1, 1, 1. Okay, all those different possible planes, they have the same indices, but they have different sign. They are under, or they belong to the same family. Now we're gonna move to something else called closed packed structure. How we can build the closed packed structure? Right. Now, if you remember, in the beginning of this chapter, what we try to do, is we try to calculate what's called the atomic packing factor, right? Atomic pack, how much of the space being filled by the atom for each unit cell. And we found that the face-centered cubic has 0.74 atomic packing factor. That means 74% of the space, available space within the unit cell being filled with atoms. This means the most efficient packing of equal sized spheres. Okay, similar for HCP, it has 0.74. Okay, so these two structures, the FCC and HCP, they are called closed packed structure. Okay, closed packed structure, because this is the most efficient way atoms or spheres with equal size can be packed together. Now we can build this material by stacking layers on top of each other. In other words, at the beginning of the chapter, we try to say we can subdivide the crystal structure into subunits called unit cell. And then if you do copy paste of those unit cells, right, you can build the material, right? Now we want to build the material by using different ways, using other ways, okay? We can say we can build this crystalline material by stacking layers on top of each other. The question, how can we do that? Well, first we're going to consider the closed packed plane, the closed packed plane in FCC and HCP. And as I just mentioned, that the 1, 1, 1 plane is considered to be the closed packed plane, is the plane with the most efficient packing in FCC, okay? And for HCP is the 0, 0, 1 plane, okay? It's called closed packed plane, okay? We're gonna take those planes, we'll try to stack them on top of each other in order to build the 3D material. Okay, things will be much simpler. Just wait for a second, okay? When we go to the next slides and the third slide, things will be much simpler than, much easier than you think right now, okay? So take it, let's try to digest it slowly, huh? Like, now, when we do the stacking, just put in your mind, we're gonna do the stacking. Stacking, that means you're gonna have a layer, and then another layer on top of it, and then another layer on top of it, okay? The stacking will be only different when we deal with the third layer that we're replacing, okay? Things will be clear in a second. Okay, now let's try to build the HCP structure, okay? Now for HCP, we'll say, imagine you have a layer of A atoms. Now the first row and the second row have A atoms, but they are not exactly aligned on top of each other. They're a little bit, spaced, okay, with a certain distance. So you see, this is the second row, this is the third row, right? So the first layer has A atoms. It's labeled A, okay? And you can notice that between them, you have some voids, right? So let's, we have void A. The first type of void is called B, right? B, okay? Where you have a vertex that's pointing up, right? So B, okay, we're gonna label them B. So all the voids that's pointing up, we're gonna call them B. The second type of void, where the vertex is pointing down, let's call it C, right? Let's call it C. Okay, great. So now what we have a layer that's called A, has A atoms, and then between those spheres of A atoms, we have two types of voids. We have B and we have C, okay? Now, if we want to place the second layer on top of the first layer, what we will do, we're gonna pick whether we're gonna place it in top of B or in top of the C void, right? It doesn't matter. Let's go with the B, okay? Let's say we're gonna have the second layer on top of the B. So the center of the atom of the second layer will be aligned with the voids B, okay? As you can see, and we're gonna label them B, okay? Now what we have A layer, okay? You have B, right? And now for the third layer, what we're gonna do, we're gonna place, now, you know, when we have the second layer, what we have, well, we have A voids, right? That's pointing down. Let's call this A, right? Which actually is aligning with the first layer, right? So we call the blue one A, right? And then the white one is still called C, right? Now we have a third layer, okay? We're gonna place it in top of A layer, okay? That will be aligned with the A layer, okay? That means you're gonna have, at the end, you're gonna have A, B, and then A again, B, and A, okay? So A, B, A, B, A, B. That means the sequence will be repeated after the second layer. So A, B, A, B. Similarly, we can say, if you have here the second layer to be in top of C, okay? And then the third layer will be on top of A. Then you're gonna have AC, AC, AC. Doesn't matter, you can call it 1, 2, 1, 2, 1, 2, or AB, 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 or AC, 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 or XY, 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 it doesn't matter. The point here is the sequence of stacking will be repeated of the second layer, okay? And that is here, this is representing the 0, 0, 1 plane, okay? So 0, 0, 1 plane, and then in the middle you have only 3 atoms, and then you have the 0, 0, 1 plane, and this is exactly, looks exactly to the unit cell that we saw when we talk about the HCP, okay? HCP, let me go back very quickly here, okay? So to show you the HCP, okay? I hope that you still remember this, okay? So we have, this is the 0, 0, 1 plane, and then in the middle you have 3, okay? And the rest of this plane, or the atoms that belong to this plane, is outside of the unit cell, okay? This one will have only 3 atoms, and then the third layer will be 0, 0, 1. So 0, 0, 1, 3 atoms in the middle, the mid plane, and then you have 0, 0, 1. Okay, great. Let me get back. So that means the stacking will be A, B, A, B. Okay, and now for FCC, let me finish. Let me draw the let me try to differentiate between HCB and FCC. Okay, now for FCC, the first layer will be the same, A. The second layer, okay, it could be B, it could be C, it doesn't matter. Let's go with B. Okay, then have A, B. Now the difference will be in the third layer. When you go to the third layer, okay? In the third layer, we're gonna place the third layer in top of the C. That means you're gonna have A, B, C, and then the stacking will repeat itself again. A, B, C, A, B, C, or we can have A, C, B, A, C, B, A, C, B, doesn't matter. The point here is the stacking will repeat itself after the third layer, okay? So we can go 1, 2, 3, 1, 2, 3. We can call it ACP, ACP, or ABC, ABC, okay? And that will build actually the one. It's not easy to visualize it for FCC here compared with CP, okay? How this is, I mean, drawing the connection between this structure and the unit cell. It wouldn't be easy, it needs more visualization, but I think it's much clearer here when you deal with the 001 plane, okay? Okay, so that is a way of building the crystalline material by stacking closed packed plane in top of each other, okay? So I'll stop here, and in next lecture, what I'll try to do, I will try to tell you that most of the material around you are not perfect. So they are not single crystalline material, okay? They are what's called polycrystalline material, and the polycrystalline material will differ also in the way that we can measure the properties, okay? So for example, polycrystalline materials, the property does not depend on direction. However, in single crystalline material or in a crystalline material, the property depends on direction, okay? So we're gonna tap on this in next lecture. I will